A multiplication algorithm is an algorithm to multiply two numbers. Depending on the size of the numbers, different algorithms are in use. Efficient multiplication algorithms have existed since the advent of the decimal system. Grid method. The grid method is an introductory method for multiple-digit multiplication that is often taught to pupils at primary school or elementary school level. It has been a standard part of the national primary school mathematics curriculum in England and Wales since the late 1990s. Both factors are broken up into their hundreds, tens and units parts, and the products of the parts are then calculated explicitly in a relatively simple multiplication-only stage, before these contributions are then totaled to give the final answer in a separate addition stage. The calculation 34, for example, could be computed using the grid, followed by addition to obtain 442 either in a single sum, or through forming the row-by-row totals plus equals 340 plus 102 equals 442. This calculation approach is also known as the partial products algorithm. Its essence is the calculation of the simple multiplications separately, with all addition being left to the final gathering up stage. The grid method can in principle be applied to factors of any size, although the number of subproducts becomes cumbersome as the number of digits increases. Nevertheless, it is seen as a usefully explicit method to introduce the idea of multiple-digit multiplications. And, in an age when most multiplication calculations are done using a calculator or a spreadsheet, it may in practice be the only multiplication algorithm that some students will ever need. Long multiplication. If a positional numeral system is used, a natural way of multiplying numbers is taught in schools as long multiplication, sometimes called grade school multiplication, sometimes called standard algorithm. Multiply the multiplicand by each digit of the multiplier and then add up all the properly shifted results. It requires memorization of the multiplication table for single digits. This is the usual algorithm for multiplying larger numbers by hand in base 10. Computers initially used a very similar shift and add algorithm in base 2, but modern processors have optimized circuitry for fast multiplications using more efficient algorithms, at the price of a more complex hardware realization. A person doing long multiplication on paper will write down all the products and then add them together. An abacus user will sum the products as soon as each one is computed. Example equals. This example uses long multiplication to multiply 23,958,233 by 5,830 and arrives at 139,676,498,390 for the result. 23,958,233, 5830. A euro, 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 71,874,699, 191,665,864, plus 119,791,165, a euro, a euro, a euro. A euro, 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 139,676,498,390. Below pseudocode describes the process of above multiplication. It keeps only one row to maintain sum which finally becomes the result. Note that the plus equals operator is used to denote sum to existing value and store operation for compactness. Equals space complexity equals, let n be the total number of digits in the two input numbers in base d. If the result must be kept in memory, then the space complexity is trivially n. However, in certain applications, the entire result need not be kept in memory and instead digits of results can be streamed out as they are computed. In these scenarios, long multiplication has the advantage that it can easily be formulated as a log space algorithm. That is, an algorithm that only needs working space proportional to the logarithm of the number of digits in the input. This is the double logarithm of the numbers being multiplied themselves. Note that operands themselves still need to be kept in memory and their n space is not considered in this analysis. The method is based on the observation that each digit of the result can be computed from right to left with only knowing the carry from the previous step. Let I and B be the ith digit of the operand, re be the ith digit of the result and psi be the carry generated for re then. A simple inductive argument showed that the carry can never exceed n and the total sum for re can never exceed dn. The carry into the first column is 0, and for all other columns, there are at most n digits in the column, and a carry of at most n from the previous column. The sum is at most dn, and the carry to the next column is at most dn/d, or n. Thus both these values can be stored in O, log n, digits. In pseudocode, the log space algorithm is electronic usage equals. Some chips implement this algorithm for various integer and floating point sizes in computer hardware or in microcode. In arbitrary precision arithmetic, it's common to use long multiplication with a base set to 2w, where w is the number of bits in a word, for multiplying relatively small numbers. To multiply two numbers with n digits using this method, one needs about n2 operations. More formally, using a natural size metric of number of digits, the time complexity of multiplying two n-digit numbers using long multiplication is I, n2. When implemented in software, long multiplication algorithms have to deal with overflow during additions, which can be expensive. For this reason, a typical approach is to represent the number in a small base b such that, for example, 8b2 is a representable machine integer. We can then perform several additions before having to deal with overflow. When the number becomes too large, we add part of it to the result or carry and map the remaining part back to a number less than b. This process is called normalization. Lattice multiplication. Lattice, or sieve, multiplication is algorithmically equivalent to long multiplication. It requires the preparation of a lattice which guides the calculation and separates all the multiplications from the additions. It was introduced to Europe in 1202 in Fibonacci's Liber Abaci. Leonardo described the operation as mental, using his right and left hands to carry the intermediate calculations. Mitraka Nanovolt plus or minus Nasu presented 6 different variants of this method in the 16th century book, al-Hisab. It was widely used in Enderun schools across the Ottoman Empire. Napier's bones, or Napier's rods also used this method, as published by Napier in 1617, the year of his death. As shown in the example, the multiplicand and multiplier are written above and to the right of a lattice, or a sieve. It is found in Muhammad ibn Musa al-Khwarizmi's Arithmetic, one of Leonardo's sources mentioned by Sigler, author of Fibonacci's Liber Abaci, 2002. During the multiplication phase, the lattice is filled in with two-digit products of the corresponding digits labeling each row and column. The tens digit goes in the top left corner. During the addition phase, the lattice is summed on the diagonals. Finally, if a carry phase is necessary, the answer as shown along the left and bottom sides of the lattice is converted to normal form by carrying tens digits as in long addition or multiplication. Example equals. The pictures on the right show how to calculate 345/12 using lattice multiplication. As a more complicated example, consider the picture below displaying the computation of 23,958,233 multiplied by 5,830. The result is 139,676,498,390. Notice 23,958,233 is along the top of the lattice and 5,830 is along the right side. The products fill the lattice and the sum of those products are along the left and bottom sides. Then those sums are totaled as shown. Peasant or binary multiplication. In base 2, long multiplication reduces to a nearly trivial operation. For each one bit in the multiplier, shift the multiplicand an appropriate amount and then sum the shifted values. Depending on computer processor architecture and choice of multiplier, it may be faster to code this algorithm using hardware bit shifts and adds rather than depend on multiplication instructions, when the multiplier is fixed and the number of adds required is small. This algorithm is also known as Peasant multiplication, because it has been widely used among those who are unschooled and thus have not memorized the multiplication tables required by long multiplication. The algorithm was also in use in ancient Egypt. On paper, write down in one column the numbers you get when you repeatedly halve the multiplier, ignoring the remainder. In a column beside it, repeatedly double the multiplicand. Cross out each row in which the last digit of the first number is even, and add the remaining numbers in the second column to obtain the product. The main advantages of this method are that it can be taught quickly, no memorization is required, and it can be performed using tokens such as poker chips if paper and pencil are not available. It does, however, take more steps than long multiplication, so it can be unwieldy when large numbers are involved. Examples. This example uses Peasant multiplication to multiply 11 by 3 to arrive at a result of 33. Decimal, binary, 11 3 10 11 11, 5 6 100 1 110, 2 12 10 1100, 124 1 11,000, a euro, 33 100,001. Describing the steps explicitly, 11 and 3 are written at the top, 11 is halved and 3 is doubled. The fractional portion is discarded. 5 is halved and 6 is doubled. The fractional portion is discarded. A figure in the left column is even, so the figure in the right column is discarded. 2 is halved and 12 is doubled. All not scratched out values are summed, 3 plus 6 plus 24 equals 33. The method works because multiplication is distributive, so. A more complicated example, using the figures from the earlier examples. Decimal, binary, 58 30 23,958,233 1,011,110,111,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,101,1 166 100 1,101,100,011 101 101 101 100 101 101 100 1457 95,832,932 10,110,110,000 101 101 101 100 101 101 100 100 728 191,665,864 1,011,011,000 101 101 101 100 100 101 101 100 100 364 383,331,728 101,101,100 101 101 101 100 101 101 100 182 766,663,456 10,110,110 101 101 101 100 101 101 100 91 1,533,326,912 1,011,011 101 101 101 100 101 101 100 100 45 3,066,653,824 100 1,100 101 101 101 100 101 101 100 22 6,133,307,648 10,110 101 101 101 100 101 101 100 11 12,266,615,296 10 11 101 101 101 100 101 101 100 100 524,533,230,592 100 101 101 101 100 101 101 100 249,066,461,184 10 101 101 101 100 100 101 101 100 100 198,132,922,368 101 101 101 100 100 101 101 100 100 a euro 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 1022143254344244435335335324322 22,210,110 139,676,498,390 111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111,111, algorithm to multiply small integers. Both base 2 long multiplication and base 2 peasant multiplication reduce to this same algorithm. In base 2, multiplying by the single digit of the multiplier reduces to a simple series of logical AND operations. Each partial product is added to a running sum as soon as each partial product is computed. Most currently available microprocessors implement this or other similar algorithms for various integer and floating point sizes in hardware multipliers or in microcode. On currently available processors, a bitwise shift instruction is faster than a multiply instruction and can be used to multiply and divide by powers of 2. Multiplication by a constant and division by a constant can be implemented using a sequence of shifts and adds or subtracts. For example, there are several ways to multiply by 10 using only bit shift and addition. X